All right, so let's get started. So as a reminder, homeworks are due today at midnight, so make sure to get your first homeworks in. And homework 2 will go out on Wednesday. And we'll talk a little bit more about homework 2 on Wednesday. It'll be pretty different from any homework you guys have ever done before, but we'll go through that next time. Yeah.
If you've done the homework by hand and you're taking pictures of your work to upload, can you put them into a single document so it's not individual pictures or files? It just makes it easier for me to grade. So just
See, that's notes from a veteran grader right there. Yeah, okay, cool. So today we're going to be talking about decision making. Yeah, so this is a way of structuring kind of like quantitative decision making into a framework that I think makes it a lot more digestible. I think it's a really useful way of thinking, even if you don't end up doing this like a lot in your own research or future work or or whatever. The process of structuring these things can be, I think, still pretty helpful. Okay, so when we think about decision making, let's go through kind of the process of doing this, and then how we can set up kind of a basic like theoretical framework, and then how that might translate into like quantitative analysis, right? And so 1, identify the objective. 2, describe the context of the decision. What are your actual decision points? So this is actually kind of important when you're setting up the framework here. I think it'll be more digestible once we get to some of the examples, but people often confuse things that are happening, let's say, probabilistically versus things that you actually have control over. And so this is going to help us really separate that out. And then thinking about uncertainty, there's almost always uncertainty. We will cover this specifically in a little bit more detail in another future lecture. In the kind of realm of decision making, like in academia, there have been a couple sort of like standardized ways of going about this. There's like a fundamental objective hierarchy, influence diagrams, and decision trees. And we're mainly going to focus on the last one, but I'll give a quick sort of example of some of these other diagrams. So fundamental objectives hierarchy, right? So this might look something like this, where your highest level objective is to like increase your lifetime earnings, right? And there are like ways you can go about doing this, right? I can increase my current salary, and that might involve me, finding a new job or getting a raise, right? And then, so you're essentially structuring your decision makings in this kind of tree based off of where they sit relative to particular decisions that you could make, right? When you organize it in this way, the higher levels of objectives can be more easily identifiable because you just go to the top, right? This also helps to identify missing objectives, and it's easy to identify things that you can measure, which are typically going to be sort of when you're achieving some of the lower level objectives. Okay? So this is kind of like a very broad, simple example just to show how you can kind of tier your objectives to structure it. Any questions about this? All right, so this is more on the sort of qualitative side. So the one we're mainly going to be focusing on is decision trees. And so this set of symbols is like a standardized notation for decision trees. And it is really important to keep the differences between these in mind because, again, this is how we're indicating things that you have control over versus, the chance events are like probabilistic outcomes. And we'll see a little bit in more detail when we get to the examples. So for the decision trees, they're read left to right. We calculate the expected value of each option, right? So does everyone know how you calculate an expected value? Nobody knows how to calculate expected value, yeah?
No.
No, okay, all right. So an expected value, so if I were to flip a coin, the chances of you getting heads is what?
0.50.
Yeah, 50%, right? So let's say that I give you $1 every time it lands on heads, but I take $1 away every time it lands on tails. What would the expected value of that be? Do you know?
I think so. The expected value that you will either give or take $1.
So let's say we flip the coin 10 times in a row. On average, what would you expect your earnings to be?
0.
Right. And so the expected value is essentially just that, kind of the average value that you're expecting from all of these bets. And so we can formalize this, right? So we said heads equals $1, tails equal, so plus $1 minus $1. So an expected value is equal to value of outcome times probability of outcome for all outcomes I. So you would sum this. So that would be, in this particular case, it would be plus 1, right, times 0.5 plus -1 times 0.5, which equals 0. Okay? So very sort of basics on probability here, but we're gonna kind of lean on sort of this concept and calculation. Okay. So let's start with our first example. So you've got a legal battle between Texaco and Pennzoil. This is actually a real court case. And you are deciding whether or not to settle. So you are, so we're taking this decision-making process from the lens of Pennzoil. So let's say we are suing Texaco for some amount of money, and Texaco offers a $2 billion settlement. Okay, so that's one thing that you could do, or you could counteroffer with $5 billion. Okay, so they say, we'll give you $2 billion, and you can either say, yes, we'll take it, or no, we want $5 billion. Okay, so what could happen if you said no, and you wanted to do this counteroffer? Well, there's some chance that Texaco could say, yes, we'll go ahead and pay that money. There's some chance that they say no, and we're going to go to court. And then there's some chance that they'll do a counter offer, and they'll settle for $3 billion. And if they decide to do this, are you going to take that offer, or are you going to go to court? And if you go to court, there's some chance that you win a lot of money, there's some chance that you win some money, and then there's some chance that you lose and you don't make any money, okay? And so, who knows what the right decision is? Hard to say without doing some sort of calculations, right? So let's go ahead and do that. Okay, so we're gonna set up a decision tree to do this. And the first thing I'm gonna do is to draw a decision node, which is a square, okay? So when you have a decision node, you get to decide the outcomes. So what are our first two decisions? Yeah, so I can choose to settle. So this is, let's say this is decision 1, and this is to settle. And the outcome here would be $2 billion. Okay? Or I can do counter offer. Counter offer. And this results in a chance node. Okay? And from here, you have a couple different outcomes. We have a 17% chance that you get $5 billion. You have a 50% chance that you go to court. And then we have a 33% chance of getting to a second decision, right? And here we're entering into another chance node. Which ones?
Like they should have equal probability of winning 5 billion or.
So here, it's these.
Oh, they're already defined.
Yeah, they're just predefined.
Okay.
Yeah. So what do you guys notice about this? These. Yeah, exactly. So anytime you have a chance node, right? All the outcomes possible out of any particular chance nodes have to add up to 1, right? And in this case, we have a similar thing. We have 20% that you win 10.3 billion. You have 50% chance that you win 5 billion. And then you have a 30% chance that you get nothing. Okay? And then in our second decision, there's a 33% chance that we get this counter offer, and then you have to decide whether or not to settle, right? And so if you settle here, then you make 3 billion, or you can choose to reject it and go to court. Okay, so this would be the same as this one here. So 20%, 50%, 30%. 30%, $0, $5 billion, and $10.3 billion. Okay, so this is the decision tree that would represent kind of this decision-making process. Is anyone confused about how we went from the example into this tree? You're kind of just working kind of left to right, right? You're going from your decision-making process and then trying to capture each of the probabilities. Okay. So the way the way that we work from here is we're kind of working on branches of the tree, okay? And you're calculating expected values back to any particular decision, and in this case, we'll actually move from right to left, even though the tree is traditionally kind of looked at from left to right. We can kind of simplify the branches, right? We would say in decision 2, what would the expected value of going to court be? How would I calculate that? Yes.
Do 5 billion times 0.5.
Yep.
Plus 10.3 billion times 0.2.
Yep. So EV of court would be 0.2 times 10.3 plus 0.5 times 5 plus, just for completeness sake, 0.3 times 0. Okay, and so if I did all of that, you would end up with 4.56 billion. So this means that on average, right, if I went to court again and again and again, then you would be expected to make $4.5 billion approximately, right, by doing this calculation. And so if that were the case, would I settle or would I choose to go to court? Choose to go to court, right? Because 4.56 billion is more than 3 billion, okay? So we're basically saying to do this in your second decision. So that effectively makes your EV here 4.56 billion. Okay? Does everyone follow? So that same calculation applies over here. So we can say EV equals 4.56. Okay? So then now I can jump back to my first decision and look at the expected value of this node. And how would I do that?
4.56 plus 0.33.
It's a probabilistic thing that this would happen, right? And so you would have to multiply.
Mhm.
And so EV of counter offer 1 would look something like 0.33 times 4.56 plus 0.5 times 4.56 plus 0.17 times 5. Okay? Does everybody follow along with that? Okay. Let me make sure that's right. Yes. Okay, so this ends up being 4.6348 billion. Okay, so this expected value is 4.63 billion. So in my first decision, should I settle or should I make a counteroffer? Right? Counteroffer, that's right. So we would choose to do this. Okay. So this kind of framework, right? We set it up, we solve for the expected values. This essentially allows us to like digest a more sort of complex decision-making process, right? And this will essentially tell us how to make decisions based off of the expected values of your outcomes. And so kind of what's coming out of the tree is how much money you'd be expecting to make, right, in each decision-making process, and therefore what decision I should make at each of these square nodes. Any questions about this?
How these probabilities are decided?
Oh, in this particular example,
Yeah, in real life.
well, okay. Well, let me just say, in this particular example, they're just kind of given and assumed, right? In real life, if you were to do something like this, right? So the actual probabilities of any particular thing happening, that could be from like historical data or from like experts' analysis, right? So sometimes you might have to make assumptions about some of the probabilities. Other times you might have something, let's say, better to go off of. But yeah, generally speaking, you're basing off of some kind of information that you have. Okay?
If we like to consider the time horizon, we just simply play with the discount rate, right?
Yeah, so, right, so when we're doing decision trees, that if the decision is operating over large time horizons, then yes, you would want to like do some kind of discounting on particular outcomes. It depends on the context of the outcome, but yeah, you certainly could do that. And then you might be operating decisions based off of like an MPV basis as opposed to these like flat values. Yeah. Okay. We'll do one more, well, we're gonna do a couple more examples, but we'll do one more on the straight up regular decision tree. Okay, who has heard of Monty Hall? Okay, who hasn't heard of Monty Hall? Okay. We're gonna do a little game, okay? So we've got 3 doors. And we've got door 1, door 2, and door 3. Behind one of these doors what is your dream car?
Lamborghini.
Okay, behind one of these doors is a Lamborghini. Behind 2 other doors is a goat. Okay? So you're either gonna get a Lamborghini or a goat.
Okay.
Okay, so I would like you to pick a door.
Now.
Yeah, go ahead, pick a door.
Number 2.
Okay, number 2. Okay. So what I'm gonna do is I'm gonna open one of the other doors, and I'm gonna open door 3 and show you there's a goat behind door 3. Okay, so knowing there's a goat behind door 3, would you like to change your answer? Would you like to switch to door 1?
I would say no.
No? Why not?
I don't know. I don't know it's half of the probability that they are like together or not.
Yeah, so so you've fallen into the classic Monty Hall trap. Sorry. So this is actually it's okay, because when this problem came out in the 70s, there were like hundreds of mathematicians who got it wrong too. So don't worry, you're in good company. So actually the correct answer for the Monty Hall problem is that you always switch doors. There's kind of an illusion where you think that it's like a 50-50 probability, but in actuality, you have a 2/3 chance of getting the right answer if you switch. And there's a couple ways that people kind of demonstrate this, right? So imagine, so one of the common ways that people show this is instead there's 100 doors instead of just 3 doors. And imagine that I will open 98 doors and show you that there are goats, right? And then I ask if you want to switch. So then the idea is that you are essentially able to choose 2 doors instead of 1 door when you do the switching. And we can show this actually with a decision tree pretty easily. And so let's do that. So this decision tree is actually a little bit trickier to set up because it's actually a little bit backwards from a traditional decision tree. But this kind of shows some of the, I guess, power of what a decision tree can do if you set it up correctly. Okay. So the chance node being at the front represents the probability that you picked the wrong door. And here's the probability that you picked the right door. So what is the probability of picking the wrong door at the beginning? 2/3, right? 2 out of 3 are incorrect, and 1 out of 3 is correct. Okay? And so regardless of which branch that I went down, I now am faced with a decision. I can either switch my door or I can not switch, right? Or let's say we'll do switch and stay. Switch and stay. So if I open the wrong door and I decided to switch, then I would get the car. But if I went down the wrong door and I decided to stay, I would I would get the goat. If I picked the right door at the beginning and I decided to switch, then I would get a goat. But if I picked the right door at the beginning and stayed, then I would get the car, right? So when you do the EV of each of the decisions, it would look something like this. So EV of switch would be 2/3 times 1 plus 1/3 times 0, right? So that's equal to 2/3. And if I stayed, the EV would be equal to 2/3 times 0 plus 1/3 times 1. Which is equal to 1/3. Okay, so you're actually twice as likely to get the car if you switch your answers. Does this make sense? Yes. You look like you have a no.
I was expecting like when you open the wrong door, like 2 by 3,
Uh-huh.
so you have like 2 options. Like when you didn't.
So like, okay, so going back to the
Okay.
original,
So
like,
it's a wrong door, then you just have to close it.
yeah, that's right. Because the trick is that the host will always show you a goat. He's never gonna open it and show you the car and be like, oh, do you wanna switch? And you'll be like, yeah, I'll choose the door with the car. Yeah. Okay, so this is kind of a odd decision tree example, right? But it can be applied to almost any sort of kind of decision-making process like this. Okay, any other questions about that?
So in case of policy making, like
Mhm.
or like project selection, let's say there is like 3 projects, and then okay, there will be like okay, authority will select like one. Okay, then that's not bringing the desired outcome. Then there will be 2 projects. If government or authority decides to like select, like discard that one, the
Mhm.
selected one, and go for like any of the other tools, then do you think it will be applicable?
Yeah, so any decision-making process where you are able to quantify like outcomes and probability of outcomes, you can apply this, right? And so this example that you're giving, it sounds like you should be able to do something like this. Okay.
Okay, thank you.
Yes. There is kind of an extension of this that we're going to talk about now. So there's a concept known as the expected value of perfect information. So this is how much you're willing to pay for information about a decision. Okay. So in our first example here, how much money would you be willing to pay someone to know the outcome of all of this upstream information, right? There is a way that we can go about sort of quantifying the value of being able to have that information. And that's what this EVPI is referring to. So let's do an example of this. Okay. So we are going to draw another decision-making tree very quickly. Okay, so I'm starting off with a decision, square node here. And so what are my possible decisions?
50%.
No. So be careful here. So out of a decision node, you should never have probabilities, right? A decision is, so this is, just to clarify, right? So decisions have to be something that you are always in complete control of, whereas chance events are the things that are out of your hands. So what can I decide to do?
Stock one.
Yeah, stock 1, stock 2, and savings, right? So we'll have something like this, stock 1, stock 2, and savings. Okay, so savings, no probabilities. I straight up will always get $500. But with both of the stocks, I will have probability nodes. You have up, flat, and down. So let's assume this is kind of like what's happening in the market, right? It can go up, it can go flat, or it can go down. And these are happening at 50, 30, 20. So 50%, 30%, 20%. And we can get $1,500, $100, and minus 1,000. And then we can get, in a more conservative stock, 1,000, 200, and minus 100. So again, I may not know immediately kind of what my sort of quote unquote correct decision would be, but I can calculate that out by setting up this decision tree. So if I do the EV of this, right, so that's 0.5 times 1,500 plus 0.3 times 100 plus 0.2 times negative 1,000. So this will equal 580. I can do the same thing here. This would be 0.5 times 1,000 plus 0.3 times 200 plus 0.2 times negative 100. If I calculate all that out, this ends up being 540. Okay? So, what do I pick?
Stock one.
Stock 1, yes, exactly. Okay. So now we can actually take this tree and modify it to do this expected value of perfect information. So given that you can make these expected values and whatnot, how much money would you be willing to pay to know if your stock is going to go up, stay flat, or go down? And the way we can actually formalize this is to flip this around. So if I start with the probability node like this, where you have up, flat, or down, it's kind of like you would be paying someone to get insider information, right? If I knew that the stock was going up or flat or down, and then I was allowed to make a decision on what I should do. So if I should do stock 1, stock 2, or savings, same thing here. So S1, S2, savings, S1, S2, savings. Okay, so if the market went up and the stock went up, I could get 1,500 in stock 1, 1,000 in stock 2, or 500 in savings. If it were flat, then I could get 1,000, 100, right? So flat in stock 1 is 100, 200 here, and 500 in savings. And then S1 would be negative 1,000, negative 100, and 500 in savings. Okay, so in this decision node, which one would I choose? Stock 1, yep. So I would go up here. In this decision, which one would I choose? Savings. So I'll go down here. And then here? Savings, exactly. Okay. And 50%, 30%, and 20%. Okay, so I could actually calculate the expected value of this node, right? So EV would be 0.5 times 1,500 plus 0.3 times 500 plus 0.2 times 500. And if I do that, my EV is 1,000. Okay, so does everyone kind of see the difference here? If I know what's going to happen, then the expected value of my decision making is a lot higher than if I didn't know what was going to happen, right? It's like the thing happens, then I get to make a decision. I mean, there's still probabilistic outcomes, right? But we can account for that, right? We're calculating only half the time you get 1,500, right? 30% of the time you get 500, and 20% of the time you're getting a guaranteed. So whatever thing happens, you're guaranteed sort of maximum payout because, let's say I have like insider trading. So how much would I be willing to pay for insider trading knowledge? What do you guys think? So if I have no insider trading knowledge, then I would be making, forgot to do this, so we would go this way. So this is our answer. So if I didn't have insider knowledge, I would make $580. If I did have insider knowledge, then I would be making $1,000. So the willingness to pay for EV, for perfect information, is equal to the difference between having that information versus not. So 1,000 minus 580 equals 420. So you would be willing to pay up to this amount of money to have that information about your outcomes. Does that make sense to everybody? Right? And if you paid this amount, right, then you would be indifferent between these two. So this is the value of your information. Yeah.
And since the 1,000, that number depends on the information, but you don't know that in advance. What
So
the information would be.
yeah, because this is the right. This is the expected value. So even though, so the idea is like, you don't know what's going to happen, but the insider guy does. So you're kind of hedging. You're like, okay, if I ask him what's going to happen, half the time he'll say, oh, the market's going to go up. 30% of the time he's going to tell you, oh, it's flat. And then 20% of the time he's going to tell you, oh, the market's actually going to go down. Does that make sense? So it's not that like he chooses your outcome, but like he can tell you with more certainty about what's going to happen. And so then you can choose the right thing to do before it happens.
You don't get the 50%, 30%, 20% from him. You come up with that yourself, and then
Yeah.
he confirms it for you which one is.
Yeah, basically,
Okay.
essentially. That's right. Okay? So this is kind of a useful extension of the decision-making tree to talk about this like value of information. Yeah.
So for the first case, we still use the percentage of 50%, 30%, and 20%.
In both cases, actually, you're still using it,
Yeah,
right?
doesn't that mean that although in the when we make a decision, so we have to think about at the moment that we make a decision, right?
Yeah.
So that,
So the idea is, so to make it easier to think about, like, you're making an investment decision today,
yeah.
and something will happen tomorrow. And the probability of those things happening are known, right? And so then, given that I know those probabilities, I can make the decision, I'm gonna make a decision today about what to do. In this case, it's still, the thing doesn't happen till tomorrow, but you can ask someone what's gonna happen tomorrow, and they'll tell you. And then you get to make the decision essentially before it happens. Yeah. Okay. So let me ask you guys realistically, if you only had one shot at this, what would you do? Would you just do the same decision? Let's say you had to invest let's say you had to invest $400 today, and tomorrow this could be your different outcomes. Okay, so forget about the EV stuff. Just like look at the numbers. Think about how you feel about these outcomes. Who would choose stock 1? Anyone? No one would choose the highest EV. Okay, who would choose stock 2? A couple people. And who would pick savings? Okay, a couple people. So why is it that we don't all just choose the highest EV thing? So someone who chose savings, you chose savings. Why would you choose savings over stock 1 and stock 2, even though the EV is higher for stock 1?
Yeah, maybe it's because it's probability.
Yeah, wait, sorry.
Oh.
Sorry. I just think the EV1 is just 580, so it's not about from $500.
Okay, yeah, and you're worried about
Yeah.
losing $1,000, right? So there's a difference, right? So if everyone could do this bet as many times as you wanted out into infinity, I think then everyone would choose stock 1, right? Because then the probability of realizing that expected value is higher. But if you have a one-off, right? So this is the biggest problem with expected value analysis. Okay. Most decisions are only played once. And so if you want to make this a little bit more realistic, you have to think about the way that we treat risk and risk attitudes. And there's actually a way to think about this. So if you're risk averse, risk neutral, or risk seeking. Okay, so a coin flip for a different amount of money can lead to really different choices, even if the expected value is the same. So we can do an example of that, okay? So, okay, Afshan. Are you willing to do a little bet with me? So if I flip a coin, if it lands on heads, you get $1, and if it lands on tails, you have to pay me $1. Is that a game that you'd be willing to play? Yeah, sure, why not, right? Expected value is 0. Okay, all right, we only get one flip. All right, now I'm gonna change the game a little bit. The expected value is still the same. Heads, I give you $100,000, but tails, you give me $100,000. We get one chance at it. Do you play the game? Yes? Okay. Who would not play the game?
No, I
Couple
mean,
few.
Yeah.
Okay.
Sometimes like.
$10 million. No, right now you get one shot at it. $10 million. You get $10 million, but if not, you gotta pay me $10 million. You can't do that. Okay, right, so see, the EV of this game is exactly the same. There's no difference, right? And so if you got to play this game 1 trillion times, sure, why not, right? But if you play it only once, our attitude towards risk is really different. So risk can change across different types of activities, as I sort of just demonstrated. Most people are actually considered to be fairly risk averse, which means that there are certain like games that have, even if you have high EVs, if the losses are really high, you might avoid doing this, right? But even if I were to characterize someone as risk averse, there are conditions in which they might be sort of risk seeking, right? And so if you were, if you're really normally like really conservative with risk, if you play the lottery, that might be kind of contrary to your typical risk seeking behavior. Like if you go gambling or something in Vegas, right? That's a negative EV. And so even characterizing people can be kind of tricky. The kind of psychology behind this is pretty famous, and so Tversky and Kahneman, if you guys have never heard of them, they are economists who demonstrated this concept of like loss aversion, right? And so the idea is that the loss in utility from losing some amount of money is often greater than getting that same amount. So we can actually do this. We can actually do this experiment. So I'm going to modify our game again. So I'm going to flip a coin. Well, actually, you have a choice now. The first one is we can play a game where I flip a coin. If I land on tails, you get nothing. But if I land on heads, you get $100. So you don't lose anything here. Or you don't have to pay me money, I should say. So you could play that game, which has an expected value of what? $50, right? So you get 0 or 100, heads or tails, right? So expected value is 50. So would you rather play that, or would you rather just be given $50? What would you do? You just want $50, right? Because it's like, it's more guaranteed, and you're like not losing out on the opportunity of having $50. Okay. What if I changed it just a little bit? Okay, so tails, still nothing, but heads, you get $101. Okay, so what's the EV? $50.5. So the EV is actually higher now. Do you take the coin flip, or do you take guaranteed 50? Okay, so you see, despite the expected value being higher, you still choose the sort of guaranteed option. And in fact, I can continue this experiment in order to elicit your personal like risk tolerance. Okay, so like $105 if I flip the coin, or guaranteed 50. What do you take?
So still, like, I would be in the safe zone.
50?
Like, if
Okay.
it goes so high.
$110. You would flip, or you would take 50? You would flip at 110? Okay.
Like, I would like go like as you move on, so like as the expected value would be higher, then I can like kind of.
Yeah. Well, the expected value was already higher at 101, right? So it's not just the EV. Okay, so the risk premium is what you'd be willing to pay to avoid the risk. So for you, it would take some positive amount of money. So your risk premium is greater than 0. Okay, and so in this particular case, we would characterize you as a risk-averse individual. What would the opposite of that be? So if I said $100 and $0 for the coin flip, and $50 guaranteed, and they would say, oh, I would take the coin flip. And you say, okay, $99 versus $50. Now your EV is actually lower, but they prefer having the higher payout, right? And so that would be a risk-seeking individual. They're like, oh, I can get $99, so I want to risk it. I want to risk my 50 to get that, right? So the certainty equivalent is the amount of certain money that you would trade in exchange for an uncertain lottery. So we can take Afshan's example. So the certainty equivalent, let's say you said no to 101, you said no to 105, but you said yes to 110. So we'll say 100, wait, I'm I'm gonna do this wrong, hang on. So the certainty equivalent is 50, right? Because that's what you're guaranteed to get, is equal to the expected value of 110. So it's 55 divided by 1 plus your RP. Okay? So simple calculation to determine your particular risk premium in this particular example. So the RP would be equal to, anyone want to help me out here?
0.1.
0.1. Okay. So this is a way that I can quantify that decision-making process of like deciding to flip the coin or take the certain amount, right? I could do that for you. I could do different examples to get like a range of RPs for you. I could do that for other people, and we can compare, right? Like who has higher or lower risk premiums, right? And so the higher this is, then the more averse I am to risk. So the more I'm willing to take that $50, even if it was 110 or 115 or 120 on the coin flip. If you're risk neutral, this value would be equal to 0, right? So if I was ambivalent, and so my EV would be 50, right? Because I always only take the $100 coin flip. So 50, then your RP would be equal to 0, okay? And if this number were smaller than 0, right? So if I were willing to take $99 or $95 or $90 on the coin flip, then you would end up with a negative RP indicating risk-seeking behavior. So the larger it is, the more risk averse, the smaller or the more negative it is, the more risk seeking. Okay. Any questions about this? So we can actually revisit our stock example. One of the ways that we can represent the value is through utility. And oftentimes the way these utility functions are these non-linear functions, okay? And so forget about the numbers here really quickly. I'll kind of demonstrate this via a sort of different example. So suppose you have no money at all. And someone were to hand you $1. Is that dollar more valuable to you if you had no money or if you had $10 million, right? So, you know, that first dollar can go really far. You might want to like buy some food to eat or whatever, right? Whereas if you had $10 million, you know, you have all the things that you want already, so having one extra dollar doesn't really make that much of a difference. So like the quantity of the dollar is the same, but the utility to me is really different, right? And so having that first dollar equates to a lot more utility, and as you have more and more amounts, as you get more and more of it, the relative amount of utility that you're getting sort of decreases. And that's actually, right, if you think about it, that's a really good way to represent in this decision-making process. We were saying like, some people were choosing savings, right? If you only had one time to make this, right? Because you're really worried about that $1,000, right? And so having an extra 1,000 to you is like less valuable than this idea that you might lose a bunch of money. And so this concept of this like nonlinear utility function helps us to essentially capture that part of the risk and decision-making process. And we can see that here, right? So you know, the first $500 is worth, let's say, 65 utils, but the next $500 is only worth 21 utils, and then the next 500 after that is only worth 14 utils. Yeah? Does that make sense to everyone? So in this particular case, you can formulate your decision trees to actually account for this. Actually, well, why don't we do it here? So I don't have to redraw the tree.
Can I ask you the utility value?
Mm-hmm.
This is not the marginal utility, I'm sorry.
Yeah, so it's just like some quantification of the like value of that money in totality. If you want to do the marginal, let's say between this and this, then you could take the difference, right? And that's what I was referring to.
Can I ask, why is the negative $100, why does the negative 100 have any utility when the negative 1,000?
Oh yeah, so we're thinking about utility on just like a relative scale. So, you know, I could, in theory, let's say, subtract like 0.4 from everything, and then that would make these ones negative and these ones positive. But the like relative amount of utility between them stays the same. So that's all you really care about is the relative amount. Yeah. Yeah. So don't let the fact that like negative ones have some positive utility worry you. Okay. So these are our profit values, but really what we care about are our utility values. Okay, and so if I were to just correspond to the values in the table, these would look actually kind of different. So this would be 1.46, 0, 0.86, 0.52, 0.33, and 0.65. Okay, this is for this one. And now I can do a calculation for, instead of the expected value, it would be the expected utility. So we'll say EU is equal to 0.5, the probability, times my utility outcome, plus 0.3 times 0.46 plus 0.2 times 0. So this would be equal to 0.638. The expected utility here would be equal to 0.5 times 0.86 plus 0.3 times 0.52 plus 0.2 times 0.33 equals 0.652, and the expected utility of this one is just 0.65. 0.65. Okay. So in this case, how does my decision change?
Top two.
Yes, exactly. So if I were doing expected value, I would take stock 1, but because I'm doing expected utility, I am going to end up choosing stock 2, right? And that takes into account our sort of risk factors for the different outcomes. Any questions? Yes.
is that really kind of possible to calculate the utility value or the dollar amount?
Yeah.
Yeah.
Yeah, absolutely. So, I was trying to build that sort of foundation up, right? These utilities are fundamentally based off of your like risk tolerance and risk premiums, right? If I were to do this and elicit, like if I were to ask this like coin flipping thing and elicit your risk premiums and that sort of thing, you could come up with some kind of utility function that would represent that. And better than just asking people, like I could actually look in the data about decisions that people or companies make and get a sense of what like a risk tolerance or risk premium would be for a particular type of like company, right? And so these, I would actually argue that this type of stuff is probably fairly well known and probably something that you could figure out. There are probably some standardized like utility functions and utility curves to help understand some of these values at different magnitudes for different types of stakeholders. Yeah, I'm making it easy. I'm just giving it to you, right? But that would be part of the challenge if you're like doing a lot of work in the decision-making space, is like either eliciting that risk and translating it into a utility function, or like finding the data to generate this yourself. Yeah, I actually think that this isn't like some kind of unknown thing. You could do this pretty, I wouldn't say easily, but definitely doable.
I'm still wondering if when we said expected like EV, so it is like driven by probability, like
Mm-hmm.
people make understand, oh, so the probability is higher and EV is higher, right?
Yeah,
To make when you do the decision making.
yeah.
But like, what is the kind of driving factor when people like choose utility, expected utility? Like why I should go for higher expected utility? So the background is risk premium?
Yes, yeah. It's based off of the true value of these things to yourself, taking into account like losses, right? And so, or the aversion to losses, right? And so, that decision tree, or the game that I was talking about where you flip the coin, right? That's like a very clear demonstration that there's a preference, right, for.
I'm just trying to understand like why I should go for EU instead of EV.
Yes, because right, so flipping a coin, get 105 or nothing versus guaranteed 50. So Afshan's decision making. In this case, my EV is equal to 52.5 versus 50. But there's something that is making us go like that, right? And that is if you were to work in your EU space, then let's say this is so the utility of coin flip is still less than the utility of guaranteed. And so the reason why we do utility instead of expected value is to better represent like a true decision-making process that values the fact that a lot of these decisions are only done once as opposed to many times, and so you may not realize your expected value when you have probabilistic outcomes, and to like capture the fact that you don't get infinite plays at this game, we do this utility thing. Does that make sense? Does that make sense to everybody? Okay.
I think it also, you can contextualize it to your own personal profile. So expected value can just be like anyone, just whoever,
Yes.
right? And utility means like, could be your utility, your utility, your utility, and so you can tune it so it's like your risk premium. So you can think of it as more like a personalized version of expected value, right? Because every, like, you think of like a company making a decision, companies have different needs in different times, and so they may need to like, even though expected value doing this would be the same, wait, we can't do that because of this, we have to like, do different discount rates. Maybe that's more
Yeah.
confusing, but yeah.
Like you can imagine, like a really simple example, like if Google or Apple has to make some kind of decision, versus if a startup were making a decision, do you think that those two companies would make the same decision if just because the expected values were the same, right? They have different risk tolerances, and so to represent that, it's not just about expected value, it's about trying to represent the behavior of those based off of the differences in their risk tolerance, which we do through utility. Okay. Our last example of the day. So this is kind of a, this was pretty eye-opening for me the first time I saw something like this. This is a way that we can think about some of the decision-making process when we combine expected values and differences in risk premiums and tolerances. Like one really salient example of this is insurance, okay? And so let's say, so you as an individual, when you purchase insurance, it's about some small probabilistic outcome, right, where something bad might happen, right? And so that kind of outcome, is that one of these things where you flip the coin once, or is that one of the things where you flip the coin 1,000,000 times? What do you guys think? Like a disaster thing that you want to insure. Yeah, exactly. So if you're only flipping the coin once, when you purchase insurance, are you operating in expected value land, or are you operating in expected utility land? Utility, right? What about the insurance company? The insurance company doesn't just see your one case, but it also sees your case, everyone, right? So the insurance company gets to like flip the coin 1,000,000 times. So are they operating in expected utility land or EV land? Right. So they can leverage this to get more money out of you. And so we'll see that here. Okay. So in this case, we're provided a utility function. Okay, so this is a nonlinear utility function that does similar things to what I've been describing about how, you know, losses are really bad and, you know, gains at really high amounts, the marginal amount that you're gaining is less and less, right? So our utility is equal to 10 times w to the 0.3. Okay. So you've got a decision to make. And this decision is that I can not buy insurance, or I can buy insurance. So I start with $2,000. And let me just set up the probability node here. Okay. So let's say it's a simple insurance. The way this works is I pay some amount for my insurance, and if something bad happens, they'll replace it. So if I were to buy insurance, what is my value here? It would be my starting $2,000 and what else? It would be minus what I pay for insurance. Okay, so we're gonna call that I. So if I'm insured, the value that I get is 2,000 minus what I spent on it. If I don't insure it, 90% of the time, nothing happens. So I get 2,000, but 10% of the time I lose some value out of that original. Let's say you got a cheap, well, that'd be a really cheap car. Let's say you have a bike and you crash 10% of the time, and you would lose $800 of that 2,000. So here you would get 1,200. Okay? So these are my raw values. And if I wanted to translate those values into utilities, then 2,000, so 10 times 2,000 to the 0.3 is equal to 97.793. 10 times 1,200 to the 0.3 is equal to 83.899. So the expected utility of this would be 96.404. Okay? So everyone see how we got this, right? It would be 0.9 times 97 plus 0.1 times 83 gives you 96. Okay. So now I can actually take this quantity and translate this back into dollars from this equation. So you're working backwards to get at W. And if you do that, this would equate to $1,906.84. Okay? Is everyone following along here? So this isn't like the expected value of these outcomes, right, which would be really different, right? right? The expected value would be 0.9 times 2,000 plus 0.1 times 1,200. This quantity of money, actually, can someone do that really quick? What's 0.9 times 2,000 plus, oh, I could probably do this in my head. Well, 1.8 plus,
1920.
yeah,
1920.
yeah, so this is equal to 1920. Okay, so you can see there's like a difference here, right? Okay, based on my expected utility value of like how I would actually make the decision-making process, what am I willing to pay for insurance here for I?
The difference?
Yes, exactly. So 2,000 minus 1906.84. This would be 93.16. Okay. So that's how much money I'm willing to pay for insurance, which notice that's higher than the expected value of what I should be paying, which is only $80, right? So for the insurer, for insurance company, so this is for individual. So what would the expected value be of me providing insurance to somebody? So if they bought insurance, right, 10% of the time, then I would have to pay $800, right, to cover that. But I would get some amount of money back, whatever they pay, plus 0.9 times I, right? So if I plug my amount that I actually pay, so this EV is positive, which means, right, if an insurance company were to break even, that means that the amount of money I'm collecting from people's insurance payments would equal the amount of damages that I'm paying out, right? But in fact, an insurance company can make more than that, specifically because you are willing to pay more than the expected value of your insurance because you are risk averse. Yeah, you don't want to experience those losses, and so you're willing to pay a little bit more than actually what you should be paying. And insurance companies can make money off of that fact, right? Because insurance companies operate in the EV space, and you operate in the utility space. Okay, any questions about that? Okay. Since we have a little bit of extra time here, this was my last example. Maybe what I'll do, since it's kind of fresh on everyone's minds with all of this stuff, is we'll actually take a quick second to talk about the second homework, which let me find some slides for. It's not in here, so. One moment. Yes, okay. Homework 2 is different from other homeworks that you guys have ever done before. Homework 2 is going to be a multiple choice homework. Okay, but in a multiple choice, right, we do something like this. So A, B, C, and D. So in a multiple choice, you say, oh, I calculated the answer. It's B, circle, done, cool. That's not how this works, okay? So instead of doing that, you will put the probability that you think B is the right answer, okay? And so let's say you do 80%, 5%, 5%, 10%. Right, and so this would give your confidence about a particular answer. Note that this all has to add up to 1. If this doesn't add up to 1, you get the problem wrong automatically, okay? So keep that in mind. The other thing is that this is like a very meta homework because it's going to test your personal risk tolerance, okay? And so what I mean is this. You'll notice that the grading is on a logarithmic scale. That means if you do this, which is an allowable answer, the maximum amount of points that you can get is 5 points to a problem, okay? If you do this and B is the right answer, great, you got 5 points. If you put 0 next to the right answer, however, if the right answer is C, you get negative infinity points. Right, so you gotta be pretty freaking tough. Okay, this is my annual reminder to everybody to never do this. Every year, for the last 7 years that I've had this homework, I tell people not to put 0, okay, next to all the answers, because if you get it wrong, you get negative infinity. So that would be failing your homework instantly. Okay, there might be a little bit of curving and fudging and everything, but don't do this. Every year someone does it, and it doesn't work out well for them. Okay, so because of the way this is scaled, right, let's say you put 80% next to the right answer, you'll get 4 out of 5, okay? But it quickly goes down, right? So if you do, if you put 40% at the right answer, you get a little less than 2 out of 5. And if you get, so it's equalized at 0.25. So if you put 25% across all of them, it's 0 points, right? So this is as much sort of strategy building into like picking the answers as it is like doing the homework. Okay. Yeah, so some people will be a little bit more conservative and put like smaller numbers next to the ones that they think are right. Some people will be, let's say, a lot more risk-seeking and put, 0.9 or 1 even next to the answer that they think is right? And so this is going to test your confidence in the answer that you're giving. Anyone have any questions about this?
this is actually confusing. So even if I have a confidence in a certain answer,
Yeah.
I have to come up with some kind of strategy to maximize score.
Yeah, and there's not a right strategy, right? Because it's all based off of your personal risk preferences and risk tolerance. I see people looking a little nervous. Yeah.
There is a way to just like do the math for the percentage, or is just
Yeah,
writing?
it's this equation right here.
Okay.
So you can figure out, and this will be posted, but you'll be able to figure out, oh, if I put like 0.85, you know, I might get like, you know, most of the,
Okay.
right? And then you can figure out like, you know, if I did something like 0.85, 0.05, 0.05, 0.05, then you might get something like, you know, 4.2 points for a right answer, and you might get like -6 for a wrong answer or something like that, right? But if you did like 0.7, 0.1, 0.1, 0.1, this might get you like 3.5 for the right answer, but you might only get like -3 for the wrong answer, or something like that, right? Yes.
So is this like one question or? Is
No.
Okay.
There's 15 questions.
Just wanna make sure.
15.
And actually,
I was like-
the last question is like very meta. So the last question asks you how many you think you got right. And then you put probabilities next to, you know, I think I got 1 to 4 right, I got 5 to 9 right, I got like 9 to something, and I got all of them right. So actually,
There's 12 questions, and then the last 3 are like.
oh yeah, stuff like
fairness,
that.
And then.
Yeah, actually, there was a student who got all the problems right and then guessed a lot more conservatively, so they thought that they got less right than they actually did, and it ended up bringing their score down to, you know, like 0. But I bet. I'm not gonna tell you guys the distribution of scores, right? But like, yeah, people go into negative, and things will get curved, right? So don't stress too much about that, right? But you know, there's different strategies about how to do this. No one will get a perfect score. Okay, that's just not gonna happen. Don't try to do that. This is as much about the strategy as actually doing the homework. Yeah. Okay. Any other questions about this? The last thing that I'll start to mention now, so I pulled up this slide from last year, so this is not the correct date. The dates are on the syllabus and posted in various places. But just to start thinking about it, the final course project, there's information posted in Canvas. So under files, there's a folder called Final Project Materials. So you can look at that. There's 3 parts to it. There's the proposal, and then there's the which will be due in a couple of weeks. You can look for the 16th.
Yes.
Okay, so one day off here. So February 16th is the proposal. You can look at some of the stuff here. Really, the idea is just to like start working on it, and it doesn't have to be set in stone. Put in the proposal, start looking into it. So myself and Peter, we will provide feedback for the project, help you guys get started, and then. So that's the first part, and then the 2 other pieces are your final project presentation and the final project report. Those are due at the end of the quarter, Don't have to worry about them yet. But start thinking about the project. It can be done in groups. So if you want to start teaming up, that's totally fine. You can do it by yourself. That's not unusual, but it's up to you guys. Yep, okay, so I will add these to the end of the slides and repost them, but start thinking about your final project. Okay, great. Thanks everyone, and that's it for today.